All right, in Tulsa, Oklahoma, 70% of the residents contracted COVID-19. That's the marginal probability of a resident of Tulsa, Oklahoma contracting COVID-19 being 70%. That's what that means. So the probability of COVID is zero point 0.7. That's the marginal. Now, that also means that the marginal probability of his complement, no COVID, is equal to 30%, 1 minus zero point 0.7, which is zero point 0.3. Okay, then it goes on to say approximately 15% of the residents with COVID got a false negative. A false negative means that they did get a negative test result, but they actually had COVID. And what they're saying is that the probability of that happening, a negative test result for somebody that had COVID, was 15%. So that's 0.15. All right. They also said that the probability of a false negative, similarly, 6% of the residents who did not have COVID-19 got a false positive. So that means that they did not have COVID, so no COVID, but they tested positive for COVID. That's a false positive. And they say the probability of a false positive is 6%. So 6% is 0.06. Okay, the question that we're being asked is if a Tulsa, Oklahoma resident is randomly selected and their COVID-19 test came back positive, so we have a condition, we already know that the test is positive. What is the probability that the patient actually has COVID-19? So they're asking us to find the probability that the patient has COVID-19 given that we already know that they tested positive. Okay, now, because of the fact that we're given negative tests given COVID and positive tests given no COVID, and this seems to be the inverted form of one of those because this has COVID given a positive test, so it's inverted, right? That means we're probably going to be using Bayes' theorem. So, in using that, what we're going to find is we're going to need to know the probability of the inverse of this. So we're inverting this. We're doing positive given COVID. That's the condition now. And we just multiply by that the probability of having COVID. In the denominator, it's the exact same thing actually. The probability of testing positive given that the person had COVID multiplied by the probability that the person had COVID. But then you have to multiply that, you have to add to that everybody who tested positive that did not have COVID. So we've included the people who tested positive and did have COVID. And now we have to include the people who tested positive and did not have COVID. So it's the probability that somebody had a positive test given that they did not have COVID. But we also have to multiply that by the probability that they did not have COVID. So this is what the Bayes' theorem formula says I need. And I need to make sure I have these things. Well, let me see. The probability of a positive test given that the person has COVID, I don't have that. The only conditionals I have are the probability of a negative test given COVID and the probability of a positive test given no COVID. What I need is the probability of a positive test given COVID. It just so happens that that's actually the complement of the probability of a negative test given COVID, because all of the people that had COVID either tested negative or tested positive, so that would be exhaustive. That would contain everybody. So that means if I want to know the probability of testing positive given that the person has COVID, all I have to do is 1 minus the probability of negative given the person has COVID, because those are complements of each other. And I already know that that's 1 minus 0.15 or 0.85. All right, so now I have everything I need, because I have now the probability of positive given the person had COVID, the probability of COVID, that's the same thing that's in the numerator, and I have the probability of a positive test given no COVID, and also the probability of no COVID. So let's plug all that in. Well, this is going to equal then 0.85, which is that probability we just found of a positive test given the person had COVID, multiplied by the probability that the person had COVID, which was 0.7, and then that's going to be divided by the exact same thing, 0.85 times 0.7, but plus, and then the other probabilities we need are the probability of a positive test given the person didn't have COVID, which is 0.06, so that's 0.06, and I have to multiply that by the probability that somebody didn't have COVID, which is 0.3, so 0.3. All right, then all we would have to do is type all this into our calculator, and when we do that, we get a result of approximately 0.9706 or 97.06% approximately.